Hi, good afternoon, everybody. It is my real pleasure to give a talk at IUMRS ICA 2021. The title of my speech today is, let me start the slideshow. Oh, the title is Advanced Techniques for the Treatment of Volatile Organic Compounds in Ambient Air through the development of functional materials based on non-photocatalysis and reactive absorption. This is basically aiming to, develop highly efficient air purifying system with the aid of various functional materials which are developed in our laboratory. Let's see how we approach our study. This is basic contents. The first part, before I start the first part, I will briefly go over the strategy, how we would carry all this study. But anyway, the basic content is first, the schematic of mini-scale air purifier system, which is generally used in a small-scale space like automobile or something like that. And using that air purifier in our second part, we'll do the performance evaluation, how the two key components of honeycomb type ceramic filter and HEPA filter for air particles to treat target VOC against our mother target formaldehyde, gaseous formaldehyde. The third part, we will modify this air purifier using the material we developed in our laboratory, which is basically a modified metal organic framework. So after modifying the air purifier, we run the same test to treat the formaldehyde and do the estimate the performance metrics like breakthrough volume and reaction kinetics, things like that, and we make comparison between the system as purchased versus the system after we modified. And then I will go over our chamber experimental video briefly, and then characterization, and finally I will go over the conclusions. So the basic strategy of our study is to begin it, purchase a mini-size commercial air purifier. As I told before, it is generally used inside the automobile. And we use this air purifier as a testing platform for the removal of VOCs, especially formaldehyde in this study, basically by adsorption or catalysis system. This commercial air purifier is made of two filter systems. First one, HEPA filter with the acronym of HP, and second part, ceramic honeycomb filter, which is also acronymed as HC. Both HP and HC filters are used to treat airborne particles and heavy VOCs, basically by HEPA filter filled with activated carbon, and light VOCs like formaldehyde by honeycomb filter. In general, HEPA filter is built to treat in a particular manner, but as they are also packed with the activated carbon, it is also good for treating heavier VOCs like benzene, toluene, things like that with the carbon number over 6. However, as activated carbon is not good for treating lighter VOCs like formaldehyde, we need some additional supporting system like honeycomb filter treated with the titanium oxide, titanium dioxide as a photocatalytic treatment system. So the third one, in this work, this AP system is used as testbed for the removal performance testing of gaseous formaldehyde between any modification of AP and after modification using the metal organic frameworks which we developed in our laboratory. So the fourth, this test is initially conducted by using air purifier as purchased with the operation of HEPA filter and honeycomb filter. And fifth and last, the relative performance between as purchased and after modification compared. So as I said, the modification is basically made using the MOF materials we synthesize in our lab using the blank honeycomb filter as well as HEPA filter. Our main goal is to make a better honeycomb filter, but for the purpose of testing, we also put this MOF material on the HEPA filter as well, although that's not the critical part. Anyway, what is most important in this study is basically air purifier. The commercial one is built with the honeycomb filter with the aid of photocatalytic system using the LED light as a UV source. However, our study in our laboratory, we developed MOF material as a non-photocatalyst or room temperature thermal catalyst. So this catalyst can operate without aid of any thermal, heating sources. So the commercial one is basically operated. Commercial one cannot be operated without LED source to reach the maximum performance. But our system can be operated even without the LED light. So that is the big difference. Can our MOF do almost same as photocatalyst or do even better than the photocatalyst? That is what we really want to see in this study. Let's see. This is the schematic of the mini-scale air purifier. We use this commercial AP system, place it inside the 17-liter size chamber, and put the sensor for formaldehyde, and provide the formaldehyde gaseous standard into this chamber, and then we operate the air purifier and check how efficiently this system removes formaldehyde between and without modification. This more details of this commercial air purifier. This air purifier runs vacuum pump to pull the air in, and the dirty air comes in and goes out as a clean air. This is upper side. This is left open feature of the this air purifier. On the upper portion, we see the HEPA filter to remove air particles. Just below, we see honeycomb filter for photocatalyst. And just below, we have a UV light source to activate photocatalyst. And just below, there is a vacuum pump to run the whole system. This unassembled part of this air purifier, we can see the light source here and vacuum pump and things like that. This more specific feature of air purifier, air pump system. It can be operated at 3 different flow rates: low, medium, and high. 100 liter per minute to 160 liter per minute. And this is UV light source. It has 4 different 1, 2, 3, 4, 3 light source in here, but basically it's controllable with the 4 different levels. There is one in addition to these 3. Now this air purifier and sensor is placed inside this chamber. You can see the honeycomb filter. And for both HEPA filter and honeycomb filter, we can modify by growing MF materials on HEPA or honeycomb filter like this. These some features of the honeycomb filter. Honeycomb filter is purchased from the manufacturer. They put some TiO2 materials here, and this honeycomb filter blank is B. No TiO2 here, just a plain pristine honeycomb filter. So we can modify using this honeycomb B system. And this 1% MnO2 U6N. This is honeycomb filter B modified using 1% of MnO2 on the U6N MOF material. This is U6N material modified one, and also the last one is U6. So this is most simple MOF U6 system we are using. This U6N is modified with a nitrogen functional group to help enhance its treatment efficiency against light VOCs like formaldehyde. And this is much more functional through the addition of 1% MnO2 to activate the catalytic efficiency as a room temperature thermal catalyst. So we expect the performance is getting better from this blank to HCU6, then U6N, and then 1% MnO2 U6N. This should be the most powerful. This strategy has been applied identically to the HEPA filter as well. This is HEPA filter blank with nothing on it. This is one is purchased. So the manufacturer has put some activated carbon on this system, and these 3 are the same modification approach as we did for the honeycomb with the U6 only and U6N, 1% MnO2, U6N. So, as I said, basically our purpose is to test the better performance of honeycomb system through the modification with the materials we developed. However, for the HEPA filter, although this is not the main goal, just for the purpose of testing performance, we also modified this system with the materials we prepared. So, based on such modification, we are using this type of acronym. HC as honeycomb type ceramic filter, HP as a HEPA filter, HCA as a honeycomb filter as purchased, HPA as a HEPA filter as purchased by the manufacturer. Acronym with the dash B implies the blank, non-treated filter for honeycomb, and HEPA filter. So using as purchased air purifier system, we ran formaldehyde at 4 different concentration: 1, 3, 5, 9 ppm, honeycomb as purchased, HEPA filter as purchased, and putting both honeycomb and HEPA filter. So this is complete system. And this is this 1/2 system. This was 1/2 system. Using these 3 different systems, we tested 4 different concentration, and then we checked the performance of each operation in terms of 3 different performance metrics. First, time of removal. So to reach 100% removal, how much time does it require? 10%, 50%, 90%, 100%. And also loaded volume. How much air should be vacuumed, treated to reach 100% or 10%? And last, reaction kinetic rate. How much formaldehyde in terms of micromole are treated per filter per operation time of hour. So as basically this formaldehyde is either removed by absorption on HPA or catalysis by HCA. We try to compare its performance in these 3 different terms. So to remove 1%, 1 ppm of formaldehyde, honeycomb as purchased showed 480 seconds to remove 100% of them. For 10%, it's 17 seconds. Also, to run 100% remover, we had to supply 1,280 liters of air into the system. But for 10% remover, 45 liters. However, for 3 ppm, 5 ppm, 9 ppm, we could not see 100% remover. It only went up to 90% or something like that. So it implies the higher concentration, the performance drops in terms of time of volume, but not too significantly. But at lowest concentration, we could see the 100% removal. So the system works more efficiently at lower concentration. Considering that formaldehyde in indoor air is generally far less than 1 ppm, and also the regulation guideline is about 0.1 ppm. So this data shows that this commercial air purifier can work very efficiently to treat lower concentration formaldehyde, which is commonly seen in ambient air or in our living conditions. Although this type of physical terms like how long it takes to reach 100% removal or how much volume is required to reach 100% is important, it is also important to see the reaction kinetics. It takes up to 10% removal, it goes 15 micromole per hour per filter. To reach 100%, it takes 5 micromole. So the efficiency is getting slower with the more removal takes place. Basically, this reaction kinetic should be expressed as amount of formaldehyde removed per time per mass of catalyst or solvent. However, it's the amount of TiO2 loaded on the honeycomb filter cannot be measured accurately at this moment. So we basically used just the filter as a replacement of the mass of catalyst. Anyway, with the honeycomb photocatalyst, the remover was, this much, was rather efficient. But this HEPA filter system, although it is mainly operated by the activated carbon, also showed some removal, although not that efficient as photocatalyst system. So, this HEPA filter is likely to support the performance of honeycomb filter. When both of them are operated together, we can see slight enhancement in performance, both time and loaded volume. But difference is not too significant, though, although we can see a general enhancement. One thing interesting is that when these two are operated together, we couldn't see 100% removal, although it went up to 90%. There was some sort of difference to treat formaldehyde with these different data sets. This is figure of the data shown in the table. We can see when 1359 ppm are treated, we can see a better removal, lower concentration, a higher concentration, and then lower concentration. The amount of formaldehyde fed into the system is much larger with the higher concentration. We can see, better removal in that respect. But there are some differences with the concentration in all diagrams. And also, we tested this performance using different flow rates. At the highest flow rate, with the closed chamber system, we see the removal takes place much quickly than the lower flow rate. Although the difference is not too significant between 100 and 130 liter. Now, most importantly, we have tested this system using the honeycomb filter after modification of MnO2 only, and U6 and U6N, and MnO2 U6N. So again, this 1% MnO2 U6N is the ultimate system we developed as a non-photocatalytic system. Even without light on, it can treat formaldehyde. Does it treat better than the honeycomb A with the light on or photocatalyst? Our result shows yes. So, like honeycomb A, it took 280 seconds, but our room temperature thermal catalyst took even shorter time, 180 seconds to remove 100%, and even far faster for 10%, 3 seconds versus 12.8 seconds. Even in reaction kinetics, we couldn't compute all, but generally when the values are computed, this best system, 1% MnO2, shows 627 micromole per hour per gram. For this part, as we synthesized, we measured per mass of catalyst. So by comparing the performance with our best system versus what is purchased, we see absolutely dominantly better performance for treating formaldehyde. So our experiment was a great success in terms of this performance comparison. And this is also showing the performance. Our best system shows the best performance here compared to what is purchased honeycomb A system. We also compared the system by this commercial one with light on empty and without light. If we compare the system with light, the remover is excellent, but without light, the performance is much lower. So, but our non-photocatalyst does the best here as well. And this, our experimental setup, and also chamber experiment. Because of short time, I'll just skip this. And this characterization research. So overall, based on this study, we were able to confirm the material we have synthesized for the air purifier was working perfectly well compared to the photocatalyst system. So it means that even without light, even without installing the LED light, we can develop very powerful catalytic system to treat formaldehyde based on our experiment. Thank you very much.